Let us look at question number 1. Equation of normal to the curve x plus y is equal to x bar y, where it cuts x axis is option A x plus y equal to 1, option B x minus y equal to 1, option C x plus y equal to 0, and option D none of this. We need to find equation of the normal to the curve x plus y is equal to x bar y, where the curve cuts x axis, At x axis we know y coordinate of the point would be 0. So when y is 0, x plus 0 is equal to x bar 0, which makes it 1. So x is equal to 1. So we need to find equation of the normal at the point 1 comma 0. The curve cuts x axis at the point 1 comma 0. For that, let us find dy by dx, differentiate with respect to x, derivative of x is 1, derivative of y is dy by dx is equal to, we need to find derivative of x power y. Let me call x power y as some u. We need to find du by dx. For that, let us take log on both sides. Log u is equal to y log x. Differentiate 1 by u du by dx is equal to y by x plus log x into dy by dx. Log x into dy by dx, or du by dx is equal to y by x plus log x into dy by dx into u is x power y. So when I call this u, du by dx I can replace it by y by x into x power y plus log x into dy by dx into x power y. So to differentiate x power y, we have used logarithmic differentiation. Now from this equation, we need to find dy by dx at the point 1 comma 0, that is when x is 1 and y is 0. So let us replace x with 1 and y with 0. 1 plus dy by dx at the point 1 comma 0 is equal to y coordinate is 0, x coordinate is 1. So this term is entirely 0. Log 1 is 0, it is 0. So this entire expression it becomes 0. So dy by dx from here we can say it is minus 1. Slope of the tangent is minus 1. So slope of the normal would be 1 minus dx by dy. So slope of normal at 1 comma 0 is minus 1. So equation of normal would be, use point slope form, y minus 0 is equal to m into x minus 1. Slope of normal would be plus 1. Product of the slopes is minus 1. So dy by dx is minus 1, minus dx by dy would be plus 1. Using point slope form, equation of the normal is y minus 0 equal to m into x minus 1, or equation is x minus y minus 1 is equal to 0. This is equation of normal. So answer is x minus y equal to 1, option B. Option B is the right answer. Next question. If y is equal to a log mod x plus bx square plus x has its extreme values at x equal to minus 1 and x equal to 2, then a comma b is option A 2 comma minus 1, option B 2 comma minus half, and C and D. We have y is equal to a log mod x plus bx square plus x. It is given that this function has its extremum values at x equal to minus 1 and x equal to 2. We know that this is continuous function and it is also differentiable in its domain. So, for a continuous and differentiable function to have extreme values, it is necessary and sufficient that f dash x to be 0. So, y dash we have to make it 0, a by x log mod x derivative is 1 by x plus 2bx plus 1 is equal to 0. It is given that this is 0 for x equal to minus 1 and x equal to 2. So, for this quadratic equation, the roots are given to be minus 1 and 2, or if we substitute minus 1 and 2, this equation will be satisfied. So, substituting minus 1 we have a minus 2b minus 1 is equal to 0, minus a minus 2b plus 1 is 0, cancelling minus 1, minus sign, a plus 2b minus 1 is equal to 0. Substituting x equal to 2, a by 2 take LCM plus 2 into 2 into 2 8b plus 2 is equal to 0. So, subtracting one equation from the other, we have 6b, a and a gets cancelled, 6b is equal to minus 3, or b is minus half, b is minus half. Substituting b value to be minus half here, a is 2. So, a is 2 and b is minus half, we can see it's option B, 2 comma minus half. Next question, f of x is equal to tan inverse of sin x plus cos x is increasing in option A minus pi by 2 to 0, option B 0 to pi by 2, option C minus pi by 4 to pi by 4, option D none of this. So, we need to check in which of the given intervals the function tan inverse of sin x plus cos x is strictly increasing. Given function is f of x is equal to tan inverse of sin x plus cos x, and we need to check the interval in which this function is increasing. So, whenever we are asked for monotonicity, do not be in a rush to differentiate. Here, observe this as a composition of two functions, tan inverse x and sin of x plus cos of x. Tan inverse x is a strictly increasing function. We all know tan inverse x is a strictly increasing function because it is inverse of tan x in minus pi by 2 to pi by 2. Tan x in minus pi by 2 to pi by 2 is a strictly increasing function. So, inverse function of a increasing function will also be increasing function. If you look at the graph of tan inverse x, this is how the graph would be. It is a strictly increasing function. So, composition of a strictly increasing function and a increasing function will be increasing, and strictly increasing function and decreasing function will be decreasing. So, f of x will be strictly increasing whenever sin x plus cos x is increasing. For f of x to be strictly increasing, sin x plus cos x should be strictly increasing. So, instead of checking monotonicity of f of x, we can call this function g of x and check monotonicity of g of x. This can be done in two ways. We can plot the graph of sin x plus cos x, divide by root 2, multiply by root 2, this is root 2 sin of x plus pi by 4. Draw the graph of root 2 sin of x plus pi by 4. Pull the graph of sin x by pi by 4 units backwards. You will get the graph of sin of x plus pi by 4. Multiply that by root 2. You will get the graph of root 2 sin of x plus pi by 4. Or alternately, you can use application of derivatives to check monotonicity of this. G dash x is equal to derivative of sin x cos x, derivative of cos x minus sin x. Now, we need to see when this cos x minus sin x is positive. To discuss sin of sin x plus cos x or sin x minus cos x or cos x minus sin x or cos x plus sin x, we need to cut the quadrant into octants. Observe in first octant, cos x values from 0 to pi by 4 will be more than the values of sin x. So, cos x minus sin x is positive. Magnitude of sin x will be more than magnitude of cos x, and both of them are positive numbers here. So, cos x minus sin x is negative. Cos x is positive, sin x is negative in this quadrant. So, cos x minus sin x would be positive. So, this is the region in which cos x minus sin x is positive, and this is the region in which cos x minus sin x is negative. So, look at the option. Option A, minus pi by 2 to 0. Minus pi by 2 to 0. F dash x is positive. G dash x is positive. So, function is strictly increasing function. Sin x plus cos x is strictly increasing from minus pi by 2 to 0. Look at option B, 0 to pi by 2. 0 to pi by 2. In 0 to pi by 2, we can see partially g dash x is positive and partially it is negative. 0 to pi by 4, g dash is positive. Pi by 4 to pi by 2, g dash is negative. Look at option C, 0 to 3 pi by 2. 0 to 3 pi by 2. 0 to 3 pi by 2. Part of the behavior function is positive. The remaining part function is negative, and the other part function is positive. So, g dash x is partially positive and partially negative. So, again it is not a strictly increasing function. So, answer is option A, minus pi by 2 to 0. Next question, if the parabola y square is equal to 4x meets a circle with center at 6, 5 orthogonally, then the possible points of intersection can be. For two curves to cut each other orthogonally, tangent at the point of intersection to one curve should be normal to the other curve. Angle between the tangent should be 90 degrees. That is, tangent to one curve is normal to the other, and tangent to the other curve is normal to this curve. So, at the point of intersection, tangent of the curve y square is equal to 4x should become normal to the circle. For orthogonal intersection, tangent to the curve y square is equal to 4x at the point of intersection should become normal to the circle. It should pass through center of the circle. Normal of any circle will pass through the center. So, let us assume the point of intersection, any point on the curve y square is equal to 4x can parametrically be assumed as, call y coordinate 2 alpha, 4 alpha square is equal to 4 alpha, 4x, x will be alpha square. So, parametrically any point on the curve y square is equal to 4x can be assumed as some alpha square comma 2 alpha. Equation of tangent at this point, we can write it as y minus 2 alpha is equal to slope of the tangent at this point given by dy by dx, parametric differentiation dy by d alpha divided by dx by d alpha. Dy by d alpha is 2, dx by d alpha is 2 alpha. So, it is 2 by 2 alpha into x minus alpha square. So, equation of the tangent to the parabola yet alpha square comma 2 alpha is given by y minus 2 alpha is equal to 1 by alpha into x minus alpha square. Okay. Now, this should become normal to the circle, that is, it should pass through center of the circle. Center of the circle is given as 6, 5. Center of the circle is given as 6, 5. So, this equation, this line, it should pass through 6, y. It should satisfy 6, y. Substitute 5 y coordinate is 5, minus 2 alpha is equal to 1 by alpha into x is 6. So 6 by alpha minus alpha square by alpha is alpha, or I can remove an alpha from here. So now I have a quadratic equation in terms of alpha. Alpha square minus 5 alpha plus 6 is equal to 0. Alpha square minus 5 alpha plus 6 is equal to 0, or alpha is, you can see the roots 3 and 2. Alpha is either 3 or it is 2. So we have two possible points of intersection. One is when alpha is equal to 2, alpha square would be 4, 2 alpha is also 4 comma 4, or when alpha is 3, 3 square is 9 and 2 into 3 it is 6, 9 comma 6. So possible points of intersection are 4 comma 4 or 9 comma 6. So we can only see 4 comma 4 there. It's option A. Next question, if f of x is equal to x power alpha log x and f of 0 is equal to 0, then the value of alpha for which Rolle's theorem can be applied for the function in closed 0 to 1 is, we have to find the value of alpha such that on the function f of x is equal to x power alpha into log x, where f of 0 is 0, we should be able to apply Rolle's theorem in the interval close 0 to 1. To apply Rolle's theorem on any function in interval a to b, there are three conditions. 1. Function should be continuous in closed interval 0 to 1. Function should be continuous in closed interval 0 to 1. Now we can see log x is a continuous function. Log x is a continuous function in open 0 to infinity. X power alpha is continuous in open 0 to infinity. So in open 0 to 1, the function x power alpha into log x is continuous, but we need continuity in closed interval 0 to 1. So limit extending to 0, because we want it to be continuous in closed 0 to 1, we need to check right continuity at 0. So right hand limit extending to 0 plus x power alpha into log x should be equal to f of 0, which is 0. As x tends to 0 plus x power alpha into log x should be equal to 0. As x tends to 0 plus, log x tends to infinity, log x tends to minus infinity. So it's an infinitely large number in magnitude. X power alpha should tend to 0 to make this 0. So for that, alpha should be strictly greater than 0. Only when power of x is positive, x power alpha into log x, it can become 0. So for the function to be continuous, alpha has to be greater than 0. So first condition what we have is alpha greater than 0. Then the function needs to be differentiable in open interval 0 to 1. The function needs to be differentiable in open interval 0 to 1. In open interval 0 to 1, log x is differentiable, x power alpha is differentiable once alpha is positive, even otherwise. So x power alpha into log x, the product will always be a differentiable function. So the function is already differentiable. And the third condition for Rolle's theorem is f of a should be equal to f of b. For the function to be applicable for Rolle's theorem in a to b, f of 0 here should be equal to f of 1. F of 0 is given as 0 and f of 1, what is it? 1 power alpha is 1 into log 1 is 0. So third condition is also automatically true, f of a is equal to f of b. Now let us look at the options. Option A, minus 2. We know alpha has to be greater than 2. So, minus 2 cannot be part of our answer. Option B, minus 1. No. Again, that is not greater than 0. Option C, 0. Even 0 is not greater than 0. So, we are only left with option D, the only positive option, which is half. So, answer is D, half. Next question. In closed 0 to 1, Lagrange's mean value theorem is not applicable to option A, f of x is equal to half minus x when x is less than half, and half minus x whole square if x is greater than or equal to half. Option B, f of x is equal to sin x by x when x is not 0 and 1 when x is equal to 0. Option C, f of x is equal to x mod x. Option D, f of x is equal to mod x. So, on these functions we have to see on which of the functions Lagrange's mean value theorem is not applicable. So, let us start from the last, option D, f of x is equal to mod x. For Lagrange's mean value theorem to be applicable in closed interval 0 to 1, the function needs to be continuous in closed 0 to 1 and differentiable in open 0 to 1. There are only two conditions which the function should satisfy. Function should be continuous in closed 0 to 1 and differentiable in open 0 to 1. Now, let us look at the function f of x is equal to mod x. Mod x is continuous in closed 0 to 1, mod x is continuous on R, and mod x is not differentiable only at 0. So, in the interval open 0 to 1, it is very much differentiable. So, mod x is both continuous in closed 0 to 1 as well as differentiable in open 0 to 1. So, LMVT, Lagrange's mean value theorem, can be applied on option D. Now, let us look at option C. F of x is equal to x mod x. F of x is equal to x mod x. With a similar logic, mod x is continuous on R, x is continuous on R, their product is continuous on R. Mod x is not differentiable at 0, but differentiable elsewhere. So, it is differentiable in open 0 to 1. X is differentiable on R, their product will be differentiable in 0 to 1. So, function is both continuous in closed 0 to 1 and differentiable in open 0 to 1. So, again Lagrange's mean value theorem can be applied on option C. Let us look at option B. F of x is equal to sin x by x if x is not 0 and 1 if x is 0. Sin x by x if x is not equal to 0 and 1 if x is equal to 0. Now, observe continuity of this function in closed 0 to 1. Sin x by x is a continuous function except at x equal to 0. Sin x by x is always continuous because sin x is continuous, x is continuous and ratio will be continuous provided 0 denominator is not 0. Now, when x is equal to 0, limit extending to 0 sin x by x is 1 and f of 0 is also 1. So, f of x is continuous at x equal to 0 as well. So, f of x is continuous on R. So, it will be continuous in closed 0 to 1. Coming to differentiability, in open interval 0 to 1, sin x is differentiable, x is differentiable. Let us look at ratio. Ratio will also be differentiable in open 0 to 1. Differentiability, there will be a problem at 0, but our investigation is only in open 0 to 1. So, in open 0 to 1, function is differentiable. So, on option B also we can apply Lagrange's theorem. So, question is on which of the functions we cannot apply Lagrange's mean value theorem. So, we are left with only option A. So, answer has to be option A. You can check either the function, it is continuous, half minus x when x is less than half is 0 in the left hand limit, function value is also 0, right hand limit is also 0, but left hand derivative is minus 1 and right hand derivative is 0. So, there is no differentiability in option A. That is the reason LMVT cannot be applied for option A. Answer is A. Next question, for what value of A does the function f of x is equal to x into a square minus 2a minus 2 plus cos x is always strictly monotonic for all x belonging to R? We need the value of a such that the function f of x is equal to x into a square minus 2a minus 2 plus cos x is strictly monotonic for all x belonging to R. For a function to be strictly monotonic, it either needs to be strictly increasing or strictly decreasing. So, for the function to be strictly increasing, f dash x should be greater than or equal to 0, equality not forming any interval. And for it to be strictly decreasing, f dash x should be less than or equal to 0 for all x belonging to R. So, f dash x should either be greater than or equal to 0 for all x belonging to R, or it has to be less than or equal to 0 for all x belonging to R. So, let us look at f dash of x. It is derivative of x is 1, a square minus 2a minus 2. Derivative of cos x is minus sin x. Now, this expression should be greater than or equal to 0 or less than or equal to 0 for all x belonging to R. A square minus 2a makes us recollect the formula of a minus 1 whole square. For that we need to have 1, we will add subtract 1 minus 3 plus sin x. This quantity should either be greater than or equal to 0 for all x belonging to R, or should be less than or equal to 0 for all x belonging to R. Let us split our discussion into two cases. One, when a minus 1 whole square minus 3 plus sin x is greater than or equal to 0 for all x belonging to R, or when it is less than or equal to for all x belonging to R. In case 1, a minus 1 whole square should always be greater than or equal to 3 plus sin x. That is, for all x belonging to R, a minus 1 whole square should be greater than or equal to 3 plus sin x. Whatever be the value of x, that is, even when sin x is maximum, a minus 1 whole square should be greater than that. So, a minus 1 whole square should be greater than the maximum most value of this 3 plus sin x, which is 4. Maximum value of sin x, we know it is 1. So, a minus 1 whole square has to be greater than or equal to 4, or a minus 1 should belong to minus infinity to minus 2 closed interval union closed interval 2 to infinity, or a should belong to minus infinity to add this 1 throughout minus 1 union 3 to infinity. Alternately, it is also possible when a minus 1 whole square minus 3 plus sin x is less than or equal to 0 for all x belonging to R. So, a minus 1 whole square has to be less than or equal to 3 plus sin x. Whatever be the value of x, a minus 1 whole square should be smaller than 3 plus sin x. That is, a minus 1 whole square should even be smaller than the least value of this function, and least value of this is 2. Sin x least value is minus 1, 3 minus 1 is 2. So, a minus 1 whole square should be less than or equal to 2 for all x belonging to R. So, a should belong to, a minus 1 should belong to minus root 2 to plus root 2, or a should belong to 1 minus root 2 closed interval to 1 plus root 2. So, for these values, when a belongs to minus infinity to minus 1 union 3 to infinity, or even when a belongs to 1 minus root 2 to 1 plus root 2, the function will be strictly monotonic. And among the options, it is not A, it is not B, it is option C, which is right. So, option C, a belongs to minus infinity to minus 1 union 3 to infinity closed interval at minus 1 and 3 is the right answer. Next question, if the curves ax square plus by square equal to 1 and a1x square plus b1y square equal to 1 intersect orthogonally Then option A, 1 by A minus 1 by B equal to 1 by A1 minus 1 by B1. Option B, 1 by A plus 1 by B equal to 1 by A1 minus 1 by B1. Option C, 1 by A plus 1 by B equal to 1 by A1 plus 1 by B1. Let us see which of the options is true. It is given that the curves ax square plus by square equal to 1 and a1x square plus b1y square equal to 1 intersect each other orthogonally. Let us say these two curves cut each other at the point alpha comma beta. Alpha comma beta is a point on the first curve and it is also a point on the second curve. So, substituting alpha comma beta in the first curve, we have a alpha square plus b beta square is equal to 1. Substituting alpha comma beta in the second curve, we have a1 alpha square plus b1 beta square is equal to 1. Then, it is given that these two curves cut each other orthogonally. That means, product of the slopes at the point of intersection is minus 1. Let us differentiate first curve to get slope of the tangent at alpha comma beta. 2ax plus 2by dy by dx is equal to 0. Differentiating 2ax plus 2by dy by dx is equal to 0, or dy by dx is equal to minus ax by by, or at the point alpha comma beta it is minus a alpha by b beta. Slope of tangent at the point alpha comma beta for the first curve is minus a alpha by b beta, and similarly for the second curve it would be minus a1 alpha by b1 beta. Only difference in these two curves is in place of a we have a1 and b we have b1. So, for the second curve slope would come out to be minus a1 alpha by b1 beta. So, product of these two slopes, because the curves cut each other orthogonally, is minus 1. From here we have a1 alpha square, a into a1 into alpha square is equal to minus of, or we can take the term this side, b1 beta square is equal to 0. a1 alpha square plus b1 beta square is equal to 0. So, effectively we have three conditions in terms of alpha, beta, a1, b1. A alpha square plus b beta square is equal to 1. a1 alpha square plus b1 beta square is equal to 1. And a1 alpha square plus b1 beta square is equal to 0. a1 alpha square plus b1 beta square is equal to 0. From these three equations, we need to eliminate alpha square and beta square. From these three equations, we need to eliminate alpha square and beta square. We can do it in many ways, one of which is subtract both the equations. We have a minus a1 into alpha square plus b minus b1 into beta square is equal to 0. Subtract from the first equation, second equation, a minus a1 into alpha square plus b minus b1 into beta square is equal to 0. Now, looking at these two equations, a1 alpha square plus b1 beta square is equal to 0 and a minus a1 alpha square b minus b1 beta square is equal to 0. We can push this the other side to get a1 alpha square is equal to minus b1 beta square. We can push this the other side to get a minus a1 into alpha square is equal to minus of b minus b1 into beta square. Now, dividing one equation by the other, we have alpha square gets cancelled, a minus a1 by a1a is equal to minus sign gets cancelled, beta square gets cancelled, b minus b1 by bb1, or in simpler terms we have 1 by a1 minus 1 by a is equal to 1 by b1 minus 1 by b, or 1 by a minus 1 by b is equal to 1 by a1 minus 1 by b1. So, it is option A. From this we have 1 by A, I can push it to the other side, 1 by A minus 1 by B is equal to 1 by A1 minus 1 by B1, which is option A. Right answer is option A. Next question, if x power 5 minus 10a cube x square plus b power 4x plus c power 5 equal to 0 has 3 equal roots, then option A, 2b square minus 10a cube b square plus c power 5 is equal to 0. Option B, 6a power 5 plus c power 5 is equal to 0. Option C, 2c power 5 minus 10a cube b square plus b power 4 c power 5 is equal to 0. And option D, b power 4 is equal to 15a power 5. Let us see, it is given that the equation x power 5 minus 10 a cube x square plus b power 4x plus c power 5 equal to 0 has 3 equal roots. Let us call this polynomial f of x. The fifth degree polynomial f of x equal to 0 has 3 equal roots. So, we can approach to this question in two ways. One, algebraically, let us assume the equal roots to be alpha, 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 remaining roots beta, gamma. We know sum of the roots, we know product of the roots, we know sum of the roots taken 2 at a time, 3 at a time, 4 at a time. From those, eliminating alpha, beta, gamma, we have the condition ready. Alternately, we can also do this question using calculus. If a function has 3 repeating roots, if a function has 3 repeated roots, then its derivative will be having the same root repeating 2 times. If f of x has a root alpha repeating m times, multiplicity of alpha with respect to f of x, if it is m, then it will be a root repeating m minus 1 times for f dash of x. So, for f dash of x, alpha will be a root 2 times. Let us say repeated root is alpha. Alpha, it is repeated root 3 times for f of x. So, it will be repeated root 2 times for f dash of x. F dash of x we can differentiate 5x power 4 minus 10a cube, derivative of x square is 2x. So, 20x into a cube plus b power 4x, derivative is b power 4, c power 5, derivative is 0. So, for this equation, that repeated root alpha is a repeated root 2 times, and because this is also a repeated root here, it will as well be a root of f double dash of x. Alpha, the repeated root of f of x, will also be a repeated root of f dash of x, and so it will also be a root of f double dash of x. So, let us see what is f double dash of x. 20x cube minus derivative of b power 4 is 0, derivative of x is 1, 20 we can take common, 20 into x cube minus a cube is equal to 0. We can see there is only one real root for this equation, that is a. So, the repeated root has to be a. X equal to a should be a root of this equation twice and should be root of this equation 3 times. So, a satisfies, a which is a root of this, satisfies this equation and also satisfies this equation. So, let me substitute a in place of x. I have a power 5 minus 10a cube into a square minus 10a power 5, the difference is minus 9a power 5 plus a b power 4 plus c power 5 is equal to 0. Minus 9a power 5 plus a b power 4 plus c power 5 is equal to 0. Let me call this equation number 1. This I got it by putting a as a root of this function. Now, a is also a root of f dash of x. A is also a root of f dash of x. Substituting a in place of x in f dash of x, we have 5a power 4 minus 20a cube into a is a power 4 minus 20a power 4 is minus 15a power 4 plus b power 4 is equal to 0. plus b power 4 is equal to 0. Let me call it equation number 2. B power 4 in first equation, once I replace it with 15a power 4, 15a power 4, then what we have is this equation becomes minus 9a power 5 plus ab power 4 is 15a power 5 plus c power 5 is equal to 0, and 15 minus 9, that is 6a power 5 plus c power 5 is equal to 0. We can see this as option B. 6a power 5 plus c power 5 is equal to 0. A is a root of f dash of x, a is a root of f of x. So, we got two conditions, and from those two conditions, replacing b power 4 with 15a power 4, we have option B as the right answer. 6a power 5 plus c power 5 is equal to 0.